Welcome to the Euclidean geometry section. Before going through this section, you should have looked through the complete trigonometry video and therefore also the videos you suggested to watch before watching the trigonometry video. Because while we won't really use trigonometry so extensively in this video, a lot of the concepts and thought process is pretty similar in Euclidean geometry. And I would say in general, Euclidean geometry is questions related to shapes put together in different arrangements. These shapes being triangles, quadrilaterals, and circles mainly. And while I'll introduce a bunch of rules that you apply to these shapes to determine various things such as certain angles, the lengths of certain sides, and so on, the best way to get really comfortable with this section is by practicing a million different questions, because you only learn the rules by head and be able to apply them to different situations once you've used them a bunch of times. That being said, here's the topics to be covered. First, I'll revise the various things you need to know from before, starting from the very basics and building up to different rules and theorems that you spent the previous years learning how to prove. But then now what will happen is, for grade 12, you can apply the results from these rules without needing to prove them again. And then you'll apply these to a bunch of new rules and theorems that you now need to learn how to prove. Next, the first topic under the new material is related to ratios and proportionality. Then we'll look at the different type of polygons you need to be familiar with. Next, we'll look in more detail at a concept known as similarity, which we've dealt with previously on a more basic level. And lastly, we'll look at the Pythagorean theorem, which is just the same as the Pythagoras theorem, just a more, fancy way of saying it. And while you're already familiar with this rule, this time we'll be learning how to prove the Pythagorean theorem by applying concepts of similarity to triangles. Let's begin. So starting off first with some revision, just to set a solid foundation before going into any new material. Firstly, what is Euclidean geometry? Euclidean geometry is defined as the study of the geometry of flat surfaces and solid figures. So flat surfaces just means basic two-dimensional shapes like triangles, rectangles, squares, circles, etc. And then solid figures refers to three-dimensional shapes such as cubes, pyramids, cuboids, and other similar figures. Just a key thing to keep in note is that when thinking about the three-dimensional figures, Euclidean geometry would exclude spheres, since their surfaces are not flat and actually curved in nature and irregular. So therefore, spheres are not included under Euclidean geometry. But you don't need to worry too much about three-dimensional figures because we won't really look at them that much in grade 12. So we'll mainly focus on two-dimensional shapes. And the first of these is triangles. So what different type of triangles are there? I'll cover two different types of classifications. The first is based on the interior angles of the triangle, meaning the angles inside of the three lines making up the shape. So the first type is acute angled triangles. And as you've heard before, acute angles are angles between 0 and 90 degrees. So in the case of acute angled triangles, all three angles are acute angles. And here's an example of one. Notice that all three angles are less than 90 degrees. And the second one is a right angled triangle. And as the name suggests, one of its interior angles is a right angle, an angle of 90 degrees, such as shown in this diagram. And then by the basic maths, since the total sum of the interior angles for a triangle is 180 degrees, that means these two angles would add up to 90. Therefore, both of them are less than 90 and are both acute angles. Then the third type is obtuse angled triangle. And the obtuse angled triangle will consist of one interior angle being more than 90 degrees. Such as the triangle shown in this diagram, where this angle is more than 90 degrees and the other two angles will be acute angles. So that's the first way of classifying triangles. Then the second way is probably the more traditional way people would think of triangles, and that's based on the relative lengths of the three sides. And the way the lengths of the three sides are will also affect the values of the interior angles, which will also be discussed. So the first type is equilateral triangles. And that's a triangle for which all three sides are the exact same length. And an implication of this is that all three interior angles are also equal. And therefore, dividing 180 degrees by 3 gives 60 degrees, which is the value for all three interior angles. And this is what an equilateral triangle will look like. And here's an important notation to keep in mind. And that's this line passing through the center of each side. And it means that every side which has this line passing through it has the same length. So in this case, that will mean all three sides have the same length. And this can be expanded upon for shapes with more than three sides, in which case, say you have two sides are the same length and the other two sides are also the same length but another length, then two of those sides would have this single line notation, and then the other two sides would also have this line notation, but there would be two lines instead. You'll see cases of this later on. Then the next type is the isosceles triangle. And for an isosceles triangle, two of the sides have the same length and the third side is a different length. And when two sides have the same length, then two of the interior angles will also be equal. And these are the angles directly opposite the two sides. So here's an isosceles triangle where this side and this side have the same length, and then the angle directly opposite both sides are also equal. Then you have the third side being some other length. Then the third type of triangle is a scalene triangle, where all three sides have different lengths and all three interior angles are also different, such as the following triangle, which has one somewhat tiny angle like this, and then one moderate angle like that. And in this case, turns out we can apply the first sort of classification we looked at, which is that this would have one obtuse angle in it. So this would be considered a scalene triangle as well as an obtuse angled triangle. So note that the two types of classifications are not independent of each other. So you can use both of them at the same time, such as in this case, where you have a scalene triangle and an obtuse angle triangle as well. Then let's look at similar triangles. So similar and similarity is a special sort of terminology to keep in mind, and two shapes are considered similar if one can be turned into the other by either resizing it, rotating it, or reflecting it. And a more formal way of saying this is, two shapes are similar if they meet the following two conditions. The first of which is all corresponding interior angles are equal, such as in the following two triangles, where you can probably notice that they have a very similar shape but just different sizes. In which case you could say that alpha could be turned into beta by resizing it. And in line with the first rule, all corresponding interior angles are equal, where in the bottom left corner you have an angle of A for both triangles, in the top corner you have an angle of B, and in the bottom right corner you have an angle of C. And the second condition is all corresponding sides are proportional, meaning they're in the same proportion, such as the following two triangles. And what we mean by proportional is if you were to take a fraction of one side in one triangle divided by the same side in the other triangle, you'd get the same value as saying another side divided by its corresponding side. And the same would apply to this third side. Therefore, A over D would be equal to B over E, which would also be equal to C over F. And I should emphasize that what these letters represent are lengths, meaning A could be a length of 5 centimeters and then D could be a length of 10 centimeters, meaning that triangle beta would be double the size of triangle alpha. Here's an example with some actual numbers, where the first triangle has sides with lengths of 1, 2, and 3. You don't need to worry about the units for now. And the second one has sides with lengths of 2, 4, and 6. And these triangles are similar because the fraction of the first side for the first triangle relative to the first side for the second triangle is 1 over 2. For the second side it's 2 over 4, and for the third side it's 3 over 6. All of which would just simplify down to 1 over 2. So that's the idea of corresponding sides being in proportion. And another thing to note is that for two shapes to be considered similar, they have to meet both conditions, meaning that all the corresponding interior angles have to be equal and all the corresponding sides need to be proportional. And since we showed that to be true for these two triangles, we can therefore say that triangle alpha is similar to triangle beta, which can be indicated like this, where you need to keep this three-line notation in mind because it's used to refer to similarity. So this would just mean triangle alpha is similar to triangle beta. So that's one important concept to know, that being similarity and similar triangles. Then another related concept is one known as congruency. And two shapes are described as being congruent if they have exactly the same shape and exactly the same size. And in the case of triangles, this would mean two triangles for which all three sides have exactly the same lengths and all interior angles are exactly the same as well, such as the following two triangles. And keep in mind the notation and terminology I've applied, which I'm bringing back from the trigonometry video, where each of the vertices of the triangle are labeled with a letter, capital letters in this case, and then also the line notation, which indicates sides of equal length. So this side and this side have the same length since they both have the single line, and this side and this side are the same length since they both have the double line, and this side and this side are the same length since they both have the triple line. And the reason a different number of lines has been used for each side is to indicate that all three sides have different lengths, meaning both of them are scalene triangles. So just to write this all down, we would say that AB is equal to DE, meaning the length of AB is equal to the length of DE, and BC is equal to EF, and lastly AC is equal to DF. So all three sides have the same lengths, and then as we can see, all three angles are also equal. So A hat is equal to D hat, and B hat is equal to E hat, and lastly C hat is equal to F hat. And since all three sides have the same lengths and all three angles are the same, we can say that the two triangles, meaning triangle ABC and triangle DEF, are congruent. And this is the sign that's used for congruency, which is pretty easy to remember because essentially two congruent triangles are exactly the same. So you can think of them as being equal to each other. So the sign for congruency is just an equal sign, but with three lines instead. Then the last thing related to triangles is the midpoint theorem. The midpoint theorem is something I think you would have looked at back in grade 10. And what it says is that a line segment joining the midpoints of two sides of a triangle is parallel to the third side and half its length. So say you have a triangle XYZ, then you have to draw the midpoints of two of the sides, let's say side XY and YZ. So again, using the line notation where the midpoint is this dot shown in black, and it would indicate that this is half and that is half. Therefore, they have the same length, and for line YZ, this is half and that's the other half. Therefore, these two sides have the same length. Then the midpoint theorem says that if you were to join the midpoints of these two sides, such as I did over here, and I labeled the ends as A and B, the midpoint theorem says that this line segment AB is parallel to the third side XZ. And the more formal way of saying this is if XA is equal to AY and YB is equal to BZ, then AB is parallel to XZ. And this two vertical line notation is used to indicate parallel lines. And it's pretty simple to understand because it's literally showing two parallel lines in it. And that's the midpoint theorem. So you need to know the theorem by head and know what it means because we will be applying it later. So that's the last bit specifically related to triangles. Then I just want to revise some basic terminology related to angles that I'll use a bunch of times throughout this video. So it's worth defining everything clearly from this early point. So the first of these is the term complementary angles. And all that means is two angles that add up to give 90 degrees, such as the following, where you can see that it's a right angle. Therefore, we know that the total of alpha and beta would be 90 degrees. Therefore, alpha and beta are complementary angles. Then the next is supplementary angles. This just refers to two angles that add up to give 180 degrees, such as the two angles alpha and beta, which form along a straight line, meaning their total would be 180 degrees. Therefore, alpha plus beta is equal to 180 degrees, and alpha and beta are supplementary angles. The next is corresponding angles, and the idea is when two lines are crossed by another line, which is line xy in the following diagram. So when two lines, meaning this line and this line in this case, are crossed by another line, line xy, the angles in the same corners are called corresponding angles. So alpha and beta are corresponding angles. And something interesting that happens is if the two original lines are parallel to each other, then the corresponding angles alpha and beta will be equal, such as shown in this diagram, where this line and this line are parallel, which is indicated using these arrows. Then the line xy forms the exact same angle in these two corners. So both corresponding angles will be equal in that case, and I just represented them using alpha for this diagram. Then the last important angle term is alternate angles, where alternate angles are angles between the two original lines and on opposite sides of line xy. So these are the two original lines, and that's line xy. So alternate angles would be between the two lines and on opposite sides of line xy, meaning A and D and B and C. So A and D are alternate angles and B and C are alternate angles. Then in a similar manner as for the corresponding angles, when the two original lines are parallel, then the alternate angles will be equal, as shown in this diagram, where these two alternating angles would both be A and these two alternating angles would both be B. Then next, let's have a look at circles.